Good afternoon, class. Today we start the first of two chapters on memory management. Here are today's topics and the chapter objectives. What's most important here for us are the first and last bullets. We're going to assume for now that a program has to be entirely within memory for the process running the program to be able to execute, and we're going to assume that processes, we have some memory protection mechanism so that a process can't overwrite another process's address space, physical address space. We already know that the CPU can only directly access registers and memory, and in a certain sense even memory access is indirect because memory can't be modified directly. Let's see, everything else here is, well, we assume that registers are accessed in a single clock cycle, and we'll add the assumption that main memory can take several clock cycles for access. So the simplest memory protection mechanism that we can use is adding a pair of registers, one holding the base of the process's memory space, and the second holding the length of that memory space. So here we're assuming that a process's memory space is contiguous, and you can see that the base register points to the base of that memory space, and the limit is the length, not the address of the last byte of that memory space. So here's how that works. Note that the process is generating physical addresses. There's no mapping of a CPU generated address before it is applied to memory. So that address is first checked against the base. If it's less than the base address, then we have a trap. Then that address is checked against base plus limit, and if it exceeds base plus limit, we have a trap. Otherwise, the address is sent on to the memory unit. Address binding can occur at compile time, link time, load time, or run time. The compile time, an example of address binding, is taking a symbolic variable name such as foo and binding it to a logical address. A compiler has to make certain assumptions such that, for example, that the program is loaded starting at address 0. Of course, if we're going to run multiple programs, that's not such a great assumption, so that the loader will take care of that by rewriting, for example, all addresses that are 0 base to the memory segment that the program is actually loaded into. If a program is composed of several separately compiled modules, then the linker will rewrite those absolute addresses, in essence placing the modules one after the other. The first module won't need to have its addresses rewritten because it is logically starting at logical address 0, but the subsequent modules will have to have their addresses edited because they are no longer starting at logical address 0, and any references between modules will have to have their addresses bound. Then when that program is actually loaded into memory to run, the loader will have to find and rewrite those addresses because now we are performing the binding from a logical address to a physical address, and most likely that program won't be loaded into memory, in the physical memory at address 0. And finally, note that all of this binding is being done at the software rather than the hardware level. So here's a summary. If the final binding is done at compile time, we're generating absolute code that cannot be moved. If the binding is done at load time, we have relocatable code, but once loaded, that program can't be moved in memory. Link time compiling or link time binding would also be a type of would be generating absolute code. And finally, if the program can be moved while executing, then we are performing binding at execution time, and that needs hardware support, as we'll see momentarily. So here's a diagram illustrating the various binding times. So the bindings that occur at this stage of compile time, the compiler generates objects. Static libraries also fall into this category. The linkage editor then takes the object modules and static libraries to form a binary. The loader will take a binary program and bind the addresses as the program is being loaded into memory. And then finally, with hardware support, we can dynamically move a program around if necessary as it's executing. When we have hardware support for this binding, then we can distinguish between logical addresses as generated by the CPU and physical addresses that are produced by a translation of a logical address via hardware mechanism. And note that the terms logical address and virtual address are synonyms. And there is no translation occurring if we do binding at compile time, link time, or load time. Logical and physical addresses will only differ if we perform the binding at execution time. So a memory management unit, or MMU, sits between the CPU and its address bus and the memory and performs this translation. The simplest mechanism is simply to use a relocation register that takes the CPU generated logical address and adds its value to produce the physical address. So here's the idea. We have the simple MMU that simply contains a relocation register value that points to, that is in essence a pointer to the beginning of the process's address space, and we're thinking of that address space as being contiguous memory. So the logical address is thought of as an offset from this. So you can see the CPU generates a logical address that goes through the MMU, and the logical address is added to the relocation register, producing the physical address. With this mechanism, the compiler can generate code starting at address 0, and the binding is made at runtime. We've talked a bit about dynamic linking already, and in fact, since shared libraries are a synonym for dynamic linking, you've dealt with this already with the syscalls project. So when static linking, the static libraries are a part of the final binary produced by the compiler and the linker. Problems with static linking are that you have multiple copies of these libraries sitting out on disk, consuming extra disk space, and if a static library changes, then all the programs that were built with those static libraries have to be recompiled. In addition, when those programs are brought into memory, you have extra copies of those libraries sitting in memory, wasting memory. So with dynamic linking, linking is actually postponed until execution time, not load time, but execution time. So the link isn't performed until that code is executed. With these stub routines take care of those details. Processes may have to be swapped if there's not sufficient available memory to run a current process. One of the complexities of swapping is, what do we do if if a process that we're going to swap out is waiting for I/O. If that I/O is being performed into the process's address space, then we have to wait for that I/O to complete before we swap the process out. Otherwise, that I/O would be performed into some other process's address space, which would be an error. So schematically, here's what's going on. Let's say that we have one memory partition for processes, so upon a context switch, we swap out the previously executing process and swap in the process that we're performing the context switch to. Context switches, however, are time-consuming enough without swapping. So this is something that isn't implemented too often. And again, we have a complication of what to do when there's pending I/O, and given the costs, and remember the swapper is the medium-term CPU scheduler. We will only swap when free memory is extremely low. Interestingly, for various reasons, swapping is typically not supported either in iOS or Android. The simplest allocation scheme is contiguous allocation, where all of processes memory is one contiguous part of memory, also known as a partition. So in the simplest scheme, main memory is two partitions, one for the kernel and one for a single process. And then base and limit registers are used to protect processes from each other, so that if a process tries to access memory outside of its partition, a trap occurs, and most likely the process is terminated. But of course, the kernel itself is allowed access to all of physical memory. So again, here's what the hardware support looks like. So the CPU generates a logical address, which is an offset to the base or relocation register. But first, that logical address is checked against the limit register, and if that logical address exceeds the limit, we get a trap. Otherwise, the logical address is added to the relocation register, forming the physical address. So again, this is the MMU function right here. Obviously, in order to multi-program the system, we need more than one memory partition. So in the view that we'll discuss here, we have partitions of variable sizes. So the partition is sized to the amount of memory needed by the process. A whole is a block of available memory. Typically, we'll have some number of holes throughout the system as processes terminate. those holes, adjacent holes, can be coalesced into larger holes. So in this example, we have 3 processes running that completely use up all of the available memory. Process 8 completes. Process 9 is started that doesn't need as much memory. Then a process 10 starts. You could imagine if process 5 now completes, we have 2 holes, and it'd be possible for a situation to occur where we want to start a process 11, which has a requirement of less than the sum of the holes, but neither hole is large enough. That's we'll see what's known as fragmentation, in this case external fragmentation, and we would have to compact memory in order to run that process. So when we have a number of holes and a new process that needs memory to be allocated to it, we have a number of algorithms we can use for fitting that process to a hole. First fit simply finds the first hole on the blink list of holes that's big enough for the process and allocate that to the process. Best fit, assuming that we keep the list of holes in sorted order, is well, first fit, except that the list of holes is in sorted order. Worst fit allocates the largest hole under the assumption that the resulting hole after the allocation will be large. So in a sense, worst fit tries to keep the hole, keep the holes from becoming too small. So external fragmentation exists between the partitions. So those are holes, and as processes are created, execute, and terminate, we can end up with a large number of small holes, and that's external fragmentation. Internal fragmentation we'll typically see more with paging systems, which we'll be discussing next time. But if a partition is allocated to a process that's somewhat larger than the amount of storage that the process actually needs, then that wastage within the partition is an example of internal fragmentation. So if external fragmentation becomes so bad that we run into the situation where we have sufficient amount of memory to run a process, but we can't run the process because that available memory is fragmented, then we have to compact, which is a process that takes time, coalescing all of the holes. And of course, if there are pending I/O operations, then we may well have to pin the process to that location, to its current location, until the I/O has completed. So segmentation is a way of splitting a contiguously allocated partition for a process into the pieces that a user thinks of. So traditionally, we have the 4 segments of a process: the program segment, the stack segment, the data segment, and the heap segment. That can be extended to smaller segments, such as some of those listed here. You can see that we have here we have the stack and arrays by going to the data segment, and the main program and the procedures could be split into subsegments, if you will. And so now each of these segments can be allocated separately, which implies that process's address space isn't contiguous anymore. And that can help with allocating space for the process. So here's the idea as a picture. We have these various memory objects, and rather than thinking of them in a contiguous chunk, we think about them separately as forming segments. And then those segments are allocated wherever there is room within physical memory. Now, note that each segment itself is allocated in a contiguous block of memory, but the segments themselves can be allocated wherever. So in a sense, what we've done is taken a partition and split it into subpartitions. Those subpartitions are known as segments. So a logical address now, instead of just consisting of an offset, consists of a segment number and an offset. That segment number is used to index a segment table, which contains two values, base value and a limit value, just as we used with the contiguous allocation method. And additionally, we need a register that points to the base of the segment table. So that would be indexed by the segment number, and then also a register that records the length of the segment table, and that will be used to check the segment number. So the segment number should not exceed the length in the length register. So in addition to the base and limit values in a segment table entry, there are a couple of control bits. Some segments might not be in use. So, for instance, if we had 3 segments in use, let's say 0, 2, and 3, and we weren't using 1, then 1's valid bit would be set to 0, and a reference to that segment would result in a trap. And in addition, there are read, write, and execute bits associated with segments. So read-only data, a read-only segment would have the read bit set with the write and execute turned off. The code segment would have execute set, probably write set to 0, and read set. So this would prevent this sort of a protection mechanism prevents read-only data from being overwritten or data from being executed, and also typically code segment from being written. So here's an example. The CPU generates a logical address, which is an ordinary 32 or 64-bit address with some of the upper higher order bits being reserved for indicating the segment number, and then the lower bits being used for the offset. So that segment number is used as an index into the segment table, producing the limit and base values. That limit is checked against the offset in the logical address, and a trap is generated as necessary. Otherwise, that offset is added to the base register value, giving us the physical address. And that finishes this first segment on memory management.